part 2 of podcast 8, Waves and Sound, and part 2 is about sound. Okay, so whenever sounds are made, we know that something vibrates, and that's what causes the sounds. And once the things vibrate, they vibrate the air, and that reaches our ear. So what vibrates when the following make the sounds? So in the violin here, it's the strings. In the tuning fork, it's the forks themselves, these parts here are the prongs, so we call them the prongs. In the drum, it's the skin of the drum which vibrates and causes the air inside to vibrate. In the man, it's his vocal cords which vibrate, causing the sound. And the last one, inside the loudspeaker, in these parts here, there's a cone. And the cone of the loudspeaker vibrates, and that vibrates air in front of it, and that causes the sound that reaches our ear. So how does sound travel? Well, we already know that sound is a longitudinal wave. And once the instrument is vibrated, or the object makes a sound, it vibrates the air in front of it. And as it moves out, the molecules are going to bump into other molecules. This is shown quite well down beneath. And they vibrate as well. And that passes the sound from the source of sound to our ear. And that causes our eardrum to vibrate. Now, this is quite a common question. How does sound travel to your ear? So you need to say something about the air vibrating. You could say something about the air molecules bumping into each other. And I would definitely say something about causing compressions and rarefactions. So definitely have air vibrating, or air molecules vibrating, bumping into each other, causing compressions and rarefactions, and they travel out from the source of sound to your ear. So we're just going to label those. There's compression, where the particles are closer together, and there's high pressure here as well. And in between then, you've got rarefactions in between. Right, you don't have to learn this, but this just shows you how the sound gets to your ear, and then your brain interprets the sound. So first of all, your ear is shaped the way it is because it's there to collect sound, and it's collected by your earlobe or your pinna. Then the sound waves travel along your ear canal. So this is the part where the wax would gather at the end. The waves make the eardrum vibrate. So the eardrum's just like a very thin skin here. It vibrates. On the other side of it are these tiny bones. They're affectionately known as a hammer, anvil and stirrup. And as the eardrum vibrates, they vibrate as well. They amplify the oscillations. That causes a vibration in this liquid, in this inner organ, which is called the cochlea. And those vibrations travel eventually to the optic nerve, the auditory nerve, and they travel to your brain, and then your brain's very clever and it can interpret those signals. They're little electrical signals, and it knows then what sounds you make. Now your brain is so clever that from a very, very early age you can recognise sounds, and your brain picks up what kinds of sounds they are. Okay, the next thing is the bell jar experiment, and the bell jar experiment is an experiment which proves that sound cannot travel through a vacuum. So this diagram here just shows an alarm clock in here, but we actually had an electrical bell in the one in the classroom, and it switched on and the bell's ringing. So if you're asked, when the bell switched on, what can you see in here? You can see the bell ringing and you can hear the bell ringing. You've got sound travelling out. And it travels through the glass. So that proves that sound's travelling through a gas and travelling through a solid before it gets out into the air and hits your ear. Turn the vacuum pump on, evacuate the air out of the jar. What can you see in here? You can still see the bell ringing, but you can't hear the sound. And why does that happen? That happens because sound can't travel through a vacuum. In other words, sound needs molecules to travel through. So sometimes people will write, sound needs air to travel through. That's not true. Sound can travel through solids, liquids and gases, and all gases, but what sound needs is particles, and in a vacuum there are no particles to travel through.